NEMA. Yeah, I can send it to the files. I think we'll do the next one and then upload everything to us. Okay.
Okay, sorry for the technical issue. Next speaker is Devojit Pal. A title of his talk is Testability of Ether Gravity near the Galactic Center Black Hole. Yes, please.
Hello everyone, my name is Devojit Pal and I am a research scholar and working under Scientific Research, and today I am presenting a topic called Testability of Ether Gravity near the Galactic Center Black Hole. Now, first, before I dive into our prime work, let us discuss some activities. Now, general relativity has been the most studied and widely accepted theory of gravity. Now, why is it so? Because it is consistent with several solar system tests so far. But the thing that arises is, why do we test the general relativity in the first place? There are several reasons. To list a few, see, black holes are the general solutions of general predictions of GR, and they automatically demand that the theory needs some modifications. And also by doing some modification to the theory, we might be able to address some problems like dark energy, dark matter, and accelerated expansion. Now, there is a formalism known as parameterized post-Newtonian formalism. This is basically a generalized formalism that we use to distinguish between several theories of gravity. Now, this is actually what actually it is the weak field limit of any metric theory of gravity. Now, this beta and gamma that you see in these equations, these beta gamma, these are actually called parameterized post-Newtonian parameters. So, for general relativity, this gamma and beta comes out to be 1. So basically, if we measure this gamma and beta, and they differ from these actual original values, then we can get a hint that there is some modification to the theory, or there might be some other theories of gravity. Now, these parameters have been measured observationally, and these are the bounds. These are actually solar system bounds given on this gamma and beta, and these are actually the galactic center bounds given in the this gamma and beta. And for solar system, that is basically given from the perihelion of Mercury near the Sun, and that is for the star S2 GC black hole system. Now, if you see carefully in these bounds compared to these bounds, these are actually quite strong bounds compared to these bounds. So you can say in the GC black hole case, the bounds are a little bit weaker compared to solar system. Now, we'll be needing this data in a little bit. Now, our actual work is FR gravity. We have studied basically FR gravity model. Now, we have studied it via two approaches. One approach is model dependent, another one is model independent. In the model dependent approach, what we do is, we just take the Einstein-Hilbert action. There is something known as Einstein-Hilbert action. and it is basically in case of GR, it has actually a function R, which is called the Ricci scalar here. But in case of FR formalism, we replace that R with FR. That is, it becomes a function of R. So in place of FR, we can in place of R, we can replace it with R to the power n. I mean that n leads to a model that we are considering. And for GR, basically we consider this FR equals to R. Then the form of potential looks something like this, and the pericenter shift that we get here, it looks something like this. But the thing why we are considering this as a model dependent, it is because if you see this delta parameter, here are two parameters, delta and RC. This delta is actually a function of n. It is purely dependent on n. So based on the model that we consider, our action also changes, and as a result, pericenter shift will also vary. Now, we in our work have considered the model R square. Now, the motivation behind considering R square model is that Starobinsky actually in the 1980s considered this model to explain primordial inflationary phase. Now, this R square model, so we have considered similarly this R square model. Now, what we have done is that we have varied the difference of, we have studied the variation of difference of two theories. That is, if you see this is Schwarzschild black hole, this GR pericenter shift, we have studied the variation of GR minus pericenter shift that I showed in the FR pericenter shift versus the variation of A. I mean, we have given a bound on A, and with respect to that, we have studied how the difference will vary, and the conclusion I will be discussing in detail. Now, see, since we are going to vary this A value, so we cannot just arbitrarily give a lower bound on A. So we have to fix that lower bound of A, and it actually comes from the observational data of the S stars rotating near the GC black hole. Now, these stars have a minimum lifetime of 6 million years. So these stars actually has to be at least 6 million years old before they can undergo, their orbit can undergo any kind of evolution. So from these bounds, and we have considered two eccentricity values, 0.1 and 0.9, to account for the minimum and maximum values of eccentricity. So from this we get an A mean value, and the A max value, that semi-major axis maximum value, that we have considered as 1000 AU, say for S2 like orbits. Now, if you look at the plots, so here is an interesting thing. See, if we vary A, so at lower values of A, we see that the difference is very small. That means this GR minus FR term is small. That means this FR term is almost comparable to GR term. So any effect of FR is, I mean, that should be detectable in compact and small orbits. And same thing happens for this. This is one for eccentricity 0.1, and this is for 0.9. And the same thing is taking place in both the plots. Now, same thing we have done for car black hole. That one was Schwarzschild. Now, same we have done for car. For car, we have 4 plots because with eccentricity in car, we have also the spin to account for. So, for 0.1 eccentricity, we have 2 spin parameters we have chosen, that is 0.1 and 0.9. So, here also we can see the same thing. For small values of A, this difference becomes small. So, that means this FR becomes comparable to the car, or in that earlier case to GR. Now, that was the model dependent approach. Now, next what we have done is we have tried to study in a more generalized way. We have gone to model independent approach. So, in this approach, the potential of the potential in FR gravity looks something like this. If you see, this almost looks like Newtonian, but there is an Yukawa type correction term with the potential. So, and here in this model independent approach, there are some predictions. This predicts some massive scalars in the theory. Now, and pericenter shift in this theory looks something like this. Now, what we have done is we have equated this pericenter shift with the PPM pericenter shift that I showed earlier, and from that we have tried to extract values of these parameters. This psi naught is a parameter in this theory. This psi naught we have tried to calculate from using the bounds on this gamma and beta that we got near the GC black hole. Now, here we have considered 3 masses of that M psi, that is scalaron masses. Now, our motivation behind choosing this specific set of mass is because this 10 to the minus 22 eV, this is actually the lower bound of scalarons, and this actually comes from the data given by LIGO observations on the gravitons, mass of gravitons. Now, as this is a massive theory, so we consider this 10 to the minus 22 eV as the lower bound of scalarons. And the upper bound of this scalars, 10 to the minus 16 eV, it was given by quantum corrections to vacuum fluctuations, and also it was given from the shadow diameter measurement of EST in the recent paper, and also calculated by Sargui, which he will be delivering in the coming day. Now, in the I am just showing you one of the cases. Here are several, because what we have done is in this equation, if you see, almost all the parameters are known. We have tried three cases for MSI, these three cases, and for these three cases, we have three values of A. We have chosen A equals to 45 AU, A equals to 100 AU, and A equals to 1000 AU. So I am just showing one of the cases, and this, if you see the plots, this is actually these two lines. This is actually the bounds on beta. I mean, one parameter, we are fixing one parameter and varying the other parameter, like that. This one is for beta, this one is for gamma, this range, and for that corresponding range we are extracting psi naught. And similarly, this one is we are simultaneously varying gamma and beta, and extracting from these plots we have extracted the value of psi naught. So psi naught, these values, these are the extracted values of our psi naught, and from this we have calculated something known as coupling constant, which is this alpha term, which is actually equal to 1 by 3 psi naught. So these are the values. Now the thing is, after we have detected all those things, see, we have to see, as these are massive scalars, we have to see that if they are affecting, if their effect is detectable or not. So that is done by something known as spinning of modified gravity. So see, these scalars that I am talking about, scalars are basically new degrees of freedom to gravity. So if they are there, then they can give rise to certain fundamental forces, and that is a problem, because in our solar system we don't encounter such forces, extra additional forces. Now this can be overcome by something known as Canadian mechanism. What it does is it actually gives dynamical properties to these scalars. They become massive in some regions, and they become very massive in some regions, and they become massless in some other regions. Now, how do we consider which are screened and which are unscreened? So this condition that psi naught by phi is less than 1, this actually says that scalars are screened. This phi is nothing but gravitational potential, less gravitational potential. That means, see, if psi naught is less than phi, that means this Newtonian potential is dominating over psi naught. So the scalars will not affect any orbit. So from this we have again plotted, and this is similar to the last case, but last case we had plotted psi naught against gamma and psi naught against beta, but this time we are plotting psi naught by phi against gamma and beta. And as you can see, this value, this is 10 to the minus 3. If you see here, it's so 10 to the minus 2. So this is actually very less than 1. So we are saying that for this m psi 10 to the minus 22, it is screened. So from this we have calculated all these cases, and we have found out that 10 to the minus 22 EV scalars, they are unscreened in case of 1000 EV, and 10 to the minus 19, it is unscreened in all the bounds that we have considered. Now, and whereas this 10 to the minus 16, it remains screened over all the bounds. Now we have done the similar measurement for a newly discovered star, short period star, S4716. It has only a period of 4 years. Now, what we have done is, for that scalars, for the same scalars, we have done the testing of screening and unscreening, and we have found that the same scalar masses, 10 to the minus 20 and 10 to the minus 19 EV, they are unscreened in the orbit of S4716. And from that, we have there is a bound on the pericenter shift of S4716. And from that, we have again tried to extract those bounds on psi naught. And from these bounds on psi naught, we again calculated pericenter shift. And this pericenter shift, if you see, this pericenter shift bound and this pericenter shift bound, I mean this pericenter shift, these are pretty much consistent, if you see. Now, everything is okay, but we have to talk about the detectability of the FR effects. If they exist, we have to talk about the detection. So what we do is, these scalars, they actually affect the pericenter shift of different stellar orbits, and this we need to check. And this we have to see by the current telescopes and the upcoming telescopes, the facilities that we have at our hands. So this is done by actually something known as astrometric shift. We check the astrometric shift, which is nothing but this pericenter shift, which is multiplied by some thing called A sin A by T. This sign, this I is actually the orbital inclination, and we are considering 90 degree because to maximize our results. And D is the distance to the GC black hole. Now the astrometric capabilities of the current ELTs that we have at hand, if you see, it is for cat it is 0.32 milliarc second, then gravity is 0.06, then TMT is 0.03. So that means if the value is above these values, if we get astrometric shift of our scalars above these values, then they should be detectable. So we check these values, and actually if you see, this is actually that I showed you in milliarc second, and this is actually in microarc second. So if you see carefully, these values actually, first of all, this is the scalar pericenter shift. This is scalar pericenter shift, and this is the GR pericenter shift. And if you see carefully, these GR pericenter shifts, they are actually within the bounds of the scalar pericenter shift. So in one way, this is actually consistent. But now, in the context of detectability, if you see, these are way above the bounds that I showed for cat gravity TMT. So they should be easily detectable by our telescope. So the same thing we did for the S4716 star also, and here also we saw that GR values and these scalar values, they are pretty much consistent, and they should be detectable by the present ELTs. So our thing is, in the future prospect of our work, we are going to study about the FR models in near our galactic center. These models, if I talk specifically, these are actually, there are several FR models, but these models, they are actually cosmologically motivated models also, because they can account for the lambda factor without bringing in some other extra parameters. So these are one of our future works, and we are planning to study these models and near binary pulsars also, and in cosmological scales also. And overall, what we see is that if our effector probability becomes comparable in GR to GR in case of very compact orbits. And also those intermediate mass scalars, that we call intermediate, because there are three masses we took. One was heavier, one was intermediate, and one was lighter. So those lighter and intermediate, they were unscreened. That means they were leaking out to the orbits of the stars and they were capable of affecting the orbits of the stars. And the present and upcoming facilities that we saw just now, that they are capable enough for probing these effects of modified gravity. And thus we can conclude that future observations using the trajectory of these stars can carry sufficient potential for testing any modified theories of gravity. So these are the references that I use.
Okay, thank you for wonderful talk. Now it's open for discussion. Yes.
Yes, my question is, as you said just now, that this can be detectable.
Yes, sir.
With this TMT and CAT.
Yes, sir.
So still now it has not been detected.
No, sir. I mean, we have to probe those orbits for any kind of effects. I mean, right now we are not probing. I mean, those telescopes are not probing for this kind of thing. So we need to probe. If these modified gravity effects exist, then we have to probe these orbits, and if they exist, then we can. I mean, certainly our telescopes are capable of detecting these orbits. I mean, these effects. So if they are there, we should detect. And if they are not there, then that would suggest that we are ready to rule out some of the modified gravity.
Is there any proposal from your side to verify?
Sir, I have just started the work in this field, so not yet, sir.
Because when you are going for such type of modeling,
Yes, sir.
so it is always important to go for observation evidence.
Yes, sir. Yes, sir.
And if that scope is there,
Yes, sir.
then you should actually propose whether some
Yes, sir.
observers can actually have that observation or not in their
Yes.
observations.
Is any more question? Yes. There is a question. Any question? No. I want to ask one question. So, as of now, we know gravity is unipolar and it is never screened out.
Yes, sir.
But in your model, gravity becomes bipolar, right?
Yes.
And it is screened out. So, as per that, in that purview, do you think of gravitational charges as well? Just in analogy with electrostatic charges.
So, that
Scalaron charges.
scalar charges. Any? I don't have that much idea.
Okay, so thank you. So, let us thank the speaker once more. Okay, thank you.
Yes.
Okay. Okay, so next speaker is the previous speaker and Bhanjar Mai Thangte. A title is Spectral Evolution of Cygnus X2.
Good evening, everyone. My name is Vanzar Moy. I'm from Mizoram University. I'm doing my PhD under the supervision of Dr. Lakshmi Zadeng and Professor Ranjit Mishra. So the talk that I'll be presenting today is Spectral Evolution of Cygnus X2. So before I go into it, this is a part of a study that we're doing right now. It's will be including only 2 observations since we are planning to publish the rest of the other observations. And also, this is what I will be talking about. This is the first Cygnus X2 observation of AstroSat. It has never been observed using AstroSat, so the result that we are getting here, the interpretation that we are doing here, it is a little bit tough, as it has as we have no paper to refer to. So it is basically based on whatever I could find from other observation like Swift, New Star, and all. So here the source that we're talking about is Cygnus X2, which is a neutron star low mass X-ray binary source, and it traces out the Z-track when we are studying it in the hardness intensity diagram. So the observation that we'll be looking into here, there is 2 observations. So this source went through all the branches of the Z-track. That is in the Z-track, we have the topmost part as the horizontal branch, the slanting part as the normal branch, and the lower part as the flaring branch. Also, the transition state between the horizontal branch and the normal branch is known as the hard apex, and the transition between the normal branch and the flaring branch is known as the soft apex. Here, of all the Z sources that we have studied, Cygnus X2 shows the most pronounced motion of the Z pattern in the HID. We have other Z pattern sources such as GX51 or GX34T0. But amongst all those, as we can see here, Cygnus X2 shows the most pronounced motion. Also, in a study carried out by Hasinger and Lamp during 1989 and 1991, it was found that the Z-track was produced by the variation of the mass accretion rate onto the compact object. Also, the Cygnus X2 is, this Z-track is a brightest group amongst low mass X-ray binary source, and it consists of a neutron star, as we have mentioned here. So in a study carried out by Ritilak in 1986, the branches were found to shift, which means that it moves along the Z-track. And this is the first indication that the Cygnus X2 shows motion of the Z-track in the hardness intensity diagram. During this time, the Cygnus X2 was not well known. So the motion along the Z-track was thought to be due to the orbital effects. But however, it has been later found, but this also it cannot be clearly confirmed. But it was later found that this variation can be due to it might be, or it is likely influenced by the mass accretion rate, or it may be due to the non-periodic motion of the sources along the track. So here, as I've said, we'll be looking into only 2 observations. I've made the slides that I have are not really that long because it has only 2 observations, and but the important part here is that it traces out the Z-track that we want to study in case of Cygnus X2 over here, and how the spectral analysis is affected according to that. So we have used LXPC and SXT on both the AstroSat satellite. So we have done it using LXPC software and the XLEC respectively, and the spectral fitting was then using expect. So here, this is the hardness intensity diagram of the first observation. Here we have taken a light curve within the energy range of 3 to 8 keV, which is the soft expression, and the 8 to 20 keV energy band, which is considered as a hard region. So here we can see that this part is a horizontal branch in the Z track. We have kept it in different states, which is HB1, HB2, and HB3. And we'll be looking into the spectral analysis of all these different states. So here, for the next observation, in this case, we have this track. So the previous one is the topmost part. As I've said, this is the horizontal branch. However, for the next branch, we have the normal branch, and this part is the soft apex, which I've talked about, which is the transition state between the normal branch and the flaring branch. Then again, we have the flaring branch, which goes from this one to this one, but then this also we have kept it separately as two states, which is the flaring branch 1 and flaring branch 2, because in these various states, we will see that from the spectral analysis, the electron temperature, the inner disk radius, changes along every part of the branch as it goes along this Z track. And so, as I've said, we have taken, for the entire energy range, we have taken 3 to 20 keV, because above that, the data points are very small and it could not be looked into properly. So we have taken only up to 3 to 20, and for SXT, 0.7 to 7 keV. So we have fitted these models, these are the first models. We have fitted it using TBAB, CH-form, Gaussian, CH-form, which is the convolution model, and this BB, the black body. And we have also used the Gaussian model. In this case, we have fixed our Gaussian to 6.4 for all the observations. So we will be, as I said, we'll be looking into the spectral analysis of all the states. In total, we will be having 8 spectra. And also, during the fitting, we have used a 3% systematic error. Okay, this is for the third one, which is the horizontal branch 3. So here we have a table over here. Here we can see that for the thermal Comptonized region, we see that we have fixed the electron temperature to be 3.50. If we do not fix this, the other parameters get a little unhinged, and we cannot get the results that we want over here. And also we have used this black body, and for here we can see from here that the inner disk temperature from the HB1 to HB3, we can see how it changes. Here it's 1.63 keV, and at the end of the horizontal branch, as we can see, the horizontal branch was slanting this way. So from the first branch to the last branch, we can see that there is a change, and it increases slightly to 1.78 keV. Also, we have calculated the inner disk radius, which is 11.54 and around 11.744. This is for only the first observation. So we have done the same for the second observation. We have used the same model for each of the states. So we have, in this case, since we have 5 states, we have 5 spectra. Looking only from the figure, we can see that there are no much change, a little bit changes, but then this is made here, over here in the table. So in this case, we can see that the inner disk temperature goes from, actually we're supposed to look from here, ND1, which is, it is from 1.7, it gradually decreases, and at the soft X, which is the region between the normal branch and the horizontal branch, we see that it is the lowest, it is 1.70 keV. Then from the FB1 and FB2, which is the lower region, FB1 was the first region, so therefore we can see that here we have 1.72 keV, and the last region we have 1.78 keV. Again, for this also, we have also calculated the inner disk radius of the source. So here, as I've said, we have used, we have 8 spectral states. I've already mentioned all this. Gaussian was kept frozen, gain correction was applied, and constant factor was also included. So here, what we can see from here is that the transition along the horizontal branch to the normal branch and then to the flaring branch is ascribed to be due to the variation of the soft black body component, which becomes stronger as it moves along the Z track. That is, from the topmost branch to the lower branch, it becomes stronger, and the thermal Comptonized region also becomes less. It also becomes less. And also we have calculated the inner radius using this formula. You can see this from the this inner disk calculation in the expect model of this BB. And so we have found it to be increasing from 9.9 to 11.5 kilometers. And also, lastly, the quantizing component is supposedly emitted by hot plasma surrounding the neutron star. I'll just give the interpretation for this one. This could be interpreted as the variation in the parameters of the black body component, which changes as it in which the inner rim of the disk changes as it moves closer to the neutron star. This is X-ray binary, so in this case we can we know that it is likely it is an accreting source. So then the donor is accreting, the accretor is taking mass from the donor. So we have a disk accretion disk over that. So the neutron star, we can this indicates that it is within the inner region of the accretion disk. So this is all that I can present for that time being. Thank you so much.
Okay, thank you so much for your interesting talk. It's now open for discussion. So any question? Yes.
So like I just wanted to know, have you checked for some cures or something like that?
We have checked that in other paper which we have already published. You can find that if you want to have the paper, you can take it from me. We have already calculated QPO, and we have got a very nice QPO which was not observed yet for AstraZeneca.
And also about this efflux, so is it absorbed or the unabsorbed? Like you have used this NEMA and the T-base model that you have used. So is it the efflux that is absorbed or unabsorbed?
In this case, we're taking the C-flux for only the additive model, so I'm not exactly sure what we are.
Like we use this like VIII, then multiplied with this C-flux, like we use this as a sum.
Yes, we use this only to fix, I cannot say exactly fix, but then to, for the additive models only. So in this case also we have kept the C-flux in front of the additive models, so we have checked for those also.
Yes.
So I see you use the norm is different in different cases.
Yeah.
Why norms is specifically properties of the source, right?
Yeah.
So why it is varying? Because it is variation of norm is dictating the inner edge radius. That is
I'm not sure, but I was thinking it might be because Cygnus X2 is a Z-type source, as we have said, and it moves continuously in the Z track. It was already observed, as I have said. So I am thinking it might be because of that, but I'll have to make sure.
Another one is you are talking about neutron star. What about the magnetic field configuration of this neutron star?
I have not looked into that yet.
We know the neutron star should be magnetized.
Yeah.
I'm not sure whether this one is a weakly magnetized neutron star. Anyway.
Yes, please.
The soft component, the topmost point. Yeah. Yeah. This is because, here we're talking about a Z-type source. So the transition along the horizontal branch, the topmost part, it's going to be looking like a Z shape only. So we have the horizontal branch, we have the normal branch, and we have the flaring branch. So the transition along those tracks can be due to the variation, it can be ascribed due to the variation in the soft blackbody component. This soft blackbody component, as we can see from the table, it becomes harder, and because of that, the thermally comptonized component becomes less. And because of that, we can from those data that we have that were given in a table, we can interpret that the emission from the inner disk radius, that is inner disk temperature. If we look into the values of the inner disk temperature, we can find that it is increasing. So it's getting harder, and the comptonization component becomes less.
Is there any more question? If no, I have just a simple question based on your last point. So I want to know whether the plasma surrounding the neutron star is weakly correlated or strongly correlated. I am interested to know whether the plasma surrounding the neutron stars is weakly correlated or strongly correlated.
I'm sorry, but I'm not sure.
I also did not understand.
Yeah.
Strongly correlated and weakly correlated.
Now, in terms of Coulombic parameter, Coulomb correlation,
I think they are strongly correlated. See, look at it. They are strongly correlated. Weakly correlated means, yeah.
it is outside. It is outside, no, in the atmosphere. Inside may be correlated, but outside, I don't know. I want to know.
I think it is strongly correlated.
Okay.
Electrons and photons can talk to each other very quickly.
Okay, thank you. So now the remaining talk of the session, it is an invited talk going to be delivered by Professor Shanarita Devi, and her title is Study of the Properties of Ultraluminous X-ray Sources in the Nearby Spiral Galaxy NGC 2276 using Chondo data.
A very good afternoon to all. Today I'll be talking on this particular galaxy NGC 2276, the properties of the ultraluminous X-ray sources we have found in this particular galaxy. And this particular presentation which I am doing, it is based on one particular work which we have done in 2021. So before going directly to the ultraluminous X-ray sources which are found in this galaxy NGC 2276, I would like to just tell a little bit about the basics of what ultraluminous X-ray sources are. And many speakers before me have mentioned a little bit about ultraluminous X-ray sources and very detailed discussion on X-ray binaries and all. So I will not be going on through those of X-ray binaries, but a little bit of what actually ultraluminous X-ray sources are and their properties, their models, and I will come directly to the ultraluminous X-ray sources of this particular galaxy itself. So ultraluminous X-ray sources, this particular word ultraluminous, why this particular word we are using is that this particular source, when it was detected somewhere around in 1989 with Einstein satellite. But the rigorous study of the properties of these kind of sources started only with the advent of Chandra satellite and XMN Newton, because these are own sources, and at the time when people started studying this kind of sources, it was like point sources and which are at very far off galaxies, external galaxies. Now we have seen recently, only somewhere around in 2020, there were some ultraluminous pulsars also in our own galaxy also. So in the definition, we have removed this extragalactic. They are found in galactic as well as extragalactic. But this particular word ultraluminous, this particular word is gauged with respect to the luminosity of the normal black hole X-ray binaries. And Professor Sankarata, he has very well explained regarding the black hole X-ray binaries. And from there, I'll just quote the luminosity. He might not have quoted, but I'll just quote the luminosity of this normal black hole X-ray binaries. Their luminosity is of the order of 10 to the power 38 arcs per second. 36 to 38, one of the speakers also have quoted. So for the ultraluminous X-ray sources, they are far more luminous than the luminosity of the normal black hole X-ray binaries. That's why this particular word ultraluminous has been used. And this one, 10 to the power, there is a convention like the lower limit of the ultraluminous X-ray sources, they are said to be at 10 to the power 39 arcs per second. Why? Because just to distinguish them from that of the this galactic black hole binaries, because never the luminosity of this galactic black hole binary reaches 10 to the power 39 arcs per second. So this particular convention of lower limit of 10 to the power 39 will just distinguish between the ultra-luminous X-ray sources and these binaries. So to be in a nutshell, just to define the ultra-luminous X-ray sources, we can define them as point sources, non-nuclear. Non-nuclear, why? They are, we just exclude those sources which are nuclear, that is the nucleus of the galaxy. So they are point sources which are non-nuclear, that is they should be a little bit far from the nucleus of the galaxy and whose luminosity is far much greater than or equal to 10 to the power 39. The law limit I have already mentioned. So this is in the energy range 0.5 to 10 keV. And sometimes the ultra-luminous X-ray sources are also termed as intermediate X-ray or intermediate luminosity X-ray objects, just to say that the luminosity is intermediate between those of X-ray binaries, and there is a range here 10 to the power 38 than between those of AGN and X-ray binaries, because for AGN is 10 to the power 42 and it can go up to 10 to the power 44 amps per second. So their luminosity range goes in between these two. That's why sometimes they are also termed as intermediate luminosity X-ray objects. Okay, before going to further slides, I would like to explain a little bit on this Eddington luminosity, because in all my future slides I will be using this particular term again and again. For an X-ray source, suppose if it is assumed to be radiating isotropically in all directions, then the luminosity is given by this particular formula, Lx equal to 4 pi r square fx, where fx is the observed X-ray flux and r is the distance to the source. So accretion, people have talked about in many of the previous slides, we have already thought about this accretion, emission from accretion peaks and all these things. So if a particular source is emitting large amount of luminosity by the process of accretion, then huge amount of luminosity can always be generated when the rate of accretion is very high. But the thing is that there should be an upper limit. In case of isotropic emission, I am saying there should be an upper limit, because the emitted or rather the generated luminosity will exert a radiation pressure outwards. Matters are being accreted onto the compact objects, whatever the black hole or the neutron stars. They are accreted because of the gravitational pull by the compact object. And now, because of this huge luminosity generated, there is a radiation pressure that is acting outwards. So what happens is that the matter that will be accreted will now experience a radiation force which is acting outwards. So there comes a limit when these two just balances each other, and we just term it as the Eddington limit. So for a particular source which is accreting isotropically, then Eddington limit is the limit when these two forces just balance each other, and the formula is given by this. So this formula you can just write here. Y is just equating those two forces, and just graph a little bit the two forces and we'll get this particular. So M is here, M is the mass of the accreting compact object. So ULX, ultra-luminous X-ray sources, people have already explained very well regarding X-ray binaries. So ultra-luminous X-ray sources, these particular sources, basically there are certain models, but basically two models I have just put here. One is isotropic emission model and another anisotropic emission. So if we just assume this ULX, ultra-luminous X-ray sources, to be emitting isotropically in all directions, then their luminosity range is such that it exceeds the Eddington limit of a 10 solar mass or sometimes 20 solar mass black hole. So if they have to have this particular luminosity, this very high luminosity, and still if we just model them to have isotropic emission, then sometimes there are certain ULX whose luminosity even crosses 10 to the power 41 ergs per second also. So the only possibility for those kind of sources is that we can model them as to harbor intermediate mass black holes. There were great debate regarding this intermediate mass black holes and this thing, but recently also somewhere around 2020 there were discovered the traditional with some intermediate mass black holes like that. So this is one possible model of the ULX. So this particular range of the black hole mass, some 100 solar mass to 10 to the power 5 solar mass, this is the one which I am talking about as intermediate mass black holes, which is intermediate between that of the stellar mass black holes and the supermassive black holes that is harbored by the active galactic nuclei. And why this bigger 10 to the power 5 upper limit? It's because if it's greater than this 10 to the power 5 solar mass, then what happens is that due to dynamical friction, this particular source will just come down to the nucleus of the galaxy. And I already mentioned about that in the non-nuclear X-ray sources. And the second model is the anisotropic emission. So in the anisotropic emission, one first particular model is that emission can be one like there is beam from a geometrically thick accretion disk, which is one very commonly used. And with this particular model, the low luminosity ULX, ultraluminous X-ray sources with order of somewhere around 10 to the power 5, some factors of 10 to the power 39 Hz per second, they can be well explained, or rather they are consistent with beaming from a high mass X-ray binary. So they are well explained with this particular model. It may be like that. The particular apparent luminosity which we are seeing is very high. It may be due to beaming from this kind of high mass X-ray binaries. And another for anisotropic emission, this is another super Eddington sources. They can also be super Eddington. I have just explained the Eddington limit. So super Eddington in Professor Santa Brothers talk also he has explained a little bit about this super Eddington sources. So if they have to have that very high luminosity, 10 to the power 39 Hz per second and above, and if they have to harbor still stellar mass black holes, then the only possibility is that they should be super Eddington accretors. And this super Eddington accretion model, there are some evidence, like here I have given in M82 ULX, one of these, in 2014 this paper has been published. This particular ULX, it was studied with data from NewStar, and there were pulsations in this ULX. So pulsations, they are property of the rotating neutron star. That means neutron stars are also there with whose apparent luminosity we are just seeing them as ULX. That means if they are neutron stars, their mass at the maximum it should go up to 2 solar mass and so on, right? So if that small mass of the neutron star has to emit this very high luminosity, then they should be super Eddington accretors. Likewise, there is also two papers in 2017 and another in 2020 also. There were ULX pulsars whose luminosity exceed the Eddington luminosity even by a factor of 500 also. So this kind of ULX, like people have modeled stellar mass black holes, emitting where this beam from geometrically thick accretion disk. Then some pulsars again, ULX pulsar. Then again another model with isotropic model, intermediate mass black holes and so on. So these are the basic models which I have just discussed here. So now I will go directly to this MCC 2276, which we have done the. Here MCC 2276 is a nearby starbus spiral galaxy. Starbus is here in this particular galaxy, the rate of formation star is very high. And this is not that very important, I have just quoted it. Here this particular galaxy MGC 2276, it was observed, my work is based on Chandra data, it was observed by Chandra ACIS ACE detector only 5 times. Here these particular 5 observations I have given the epoch 1, 2, 3, 4 and 5, we have just labeled it. And one more thing is that the distance of this particular galaxy, one paper in 2019 has quoted is 41 megaparsec and another in 2015 has quoted is 32.9 megaparsec. We have just averaged it out and we have just taken the average value 36.95 for the present curve. So this particular galaxy, which was observed in 5 epoch, what we will be doing in this particular work is the first 2 epoch. It was well studied by this paper, this 2019 and 2015 paper. So we will not be doing much with these first 2 observations. Rather, our study will be focused on these last 3 observations. And whatever the result we will be getting out of these 3 observations, we will compare with whatever they have got in the earlier observations. The first 2 observations were one in 2004 and another in 2013. The last 2 in 2019 and 2 observations in 2020. So we'll just compare the latest 3 observations with that of the previous 2 observations. So it's a period of somewhere around 16 years from the first observation till the last one. Okay, data analysis, I will not go through that much. We have, since this is Chandra data, we have used CIO, Chandra Interactive Analysis of Observation, the calibration data distributed with that, and Kiasol. So let me just, okay, the steps, it's not that important. I'll just skip the steps. We, from the event file, level to event file, that is a clean event file, we have just generated the sources, the list of the sources, and we have selected some sources. How we have selected is that we have selected those sources whose counts, total counts is like 200 or more, so that we can do a proper spectral fit of the sources. So these are the properties of the X-ray point sources. Source 1, I have given the position. This is of nuclear distance. Then this is not important. These are the count and count rate. Here we can see that this source, I have just focused, I have told you, I have just focused on the last 3 observations. The counts over here are not very high. Somewhere around 82, that we'll just check whether the proper fitting can be done. It's not that good, then we can always discard. At the maximum, it goes up to only somewhere around 313, so we cannot just think of taking very complex models here. And one more thing is that the count rate over here is very low. It's always less than 0.05, and we can be very much sure that the sources we have taken here are all pile up. They are not pile up affected because of the low count rate. And we have also made sure that for each and every source, when we were taking the background region area, we will make sure that the background is not that much, not much diffuse emission is there over there, and it's not contaminated. And here, since the sources are having not very high count rate, we have just tried the 2 empirical models, display body model and the power law model. Why I have just chosen display body and power law model? The emission mechanism already, previous speakers have already explained the physics behind the emission mechanism of all those things. So this is the, okay, it's very small. I don't know whether it will be very visible from the back side. So here is the spectral properties of those point sources as stated by the 2 models. Here, for the source 1, this is for the power model and this is for the display model. I will not focus on each and everything, but here I would like to try to focus on the luminosity which I have got here, and the luminosity over here. This is the inner disk temperature, the temperature of disk annulus from where this particular spectrum can be thought to be generated from. So these particular formulas, we can see that all the sources have their luminosities better than 10 to the power 39, and most of them, around 5 of them, have more than 10 to the power 40 arcs per second. So all of them are ULX, ultra luminous X-ray sources, and 5 of them we can, within error bar we have checked, and it is above 10 to the power 40 arcs per second, which is a subclass which we call it as the extremely luminous X-ray sources, ELX. So here, source-wise, I have just checked the change in the luminosity of these sources. This first source, source 1, it is in the ELX regime. Then its luminosity has decreased a little bit by 10 to the power 39. Then again in the last 3 books, the first 2 books, 1 and 2, we have referred from these 2 works, which people have already done, and these last 3 books, it's from the result of our work which we have done. Though even though for source 1 it has reduced in the second epoch, which was observed in 2013, in the 2019 and 2020 epoch observation, their luminosity has again increased up to ELX regime. And this particular luminosity, they are persistent in all the 3 epochs. Likewise for source 2, it's a very interesting object. You can see this is 10 to the power 38. That is the binary range. Then it has entered the ULX region. Then the ELX region. Likewise for other sources also, where this one 39, 39, 40, then 40, 40, 40 with a decline of somewhere around 10 to the power 39 in the last number 5. Then 40, 40, 40. Again here for source 6 and 7, in the first epoch it is 10 to the power 38. Then in epoch 3 is 10 to the power 39. But for source 6, it's still in 10 to the power 39 in epoch 3, and but slightly increased in the latter epoch. Likewise for source 7 also, binary ULX region, then ELX region. So what we can say, okay, graphically I have just represented this one like this. So what we can have the explanation regarding this is that for a luminosity to vary like this by some factor, 2, 3 factor, 2, 3, even 5, 6 factor, in years it may be because of tidal effects and mass transfer rate. For example, if you have a black hole and it is fed by some strong wind from a nearby very massive star, then the mass transfer rate can always be variable. It can vary because it's not a stable process, and the variability may lead to mass accretion rate variation and hence the variation in the luminosity. So this is long-term variability of the sources. Now let's come to the short-term variability of the sources. For all the southern sources, we have extracted the light curve. Here I have shown only the light curve for 2000. If you can see, it's only 2000 seconds, that is 2 kiloseconds. What we have done is that we have just extracted the light curve for all the southern sources in all these particular beams, 0.5 kiloseconds, 1 kilosecond, 2 kilosecond and 4 kilosecond. And here for a source to be defined as variable, then the null hypothesis probability that the count rate is constant during the observation is less than 1. That means the source is variable with a significance of greater than 99%. But for all of these sources in all these bins, 0.5, 1, 2, 4 kiloseconds, this probability was all greater than 11%. So this is a signature that all these 7 sources are not variable in the kilosecond time scales. That is, short-term variability is totally absent in these 7 sources. However, long-term variability was there. So just for a rough estimate of the black hole mass of these 7 sources, what we have done is that, okay, this was already explained in one of the talks. For the non-rotating, this one, Schwarzschild black hole, the innermost stable circular orbit is at 3 times Rs, where Rs is the Schwarzschild radius. And for spinning curve, this one 0.5 to 4.5. But for us, for a rough estimate of black hole mass, we have taken the inner disk radius from where the emission is being emitted. We have just taken at 10 times Gm by c square, a little bit higher than that of the innermost stable circular orbit. And we have estimated the black hole mass, and it was found that all the 7 sources, they are found to harbor only stellar mass black holes. Maximum was 70, somewhere around 70 solar mass only. So it was like only stellar mass black holes, and hence that very high luminosity should be due to superintendent accretion rate. If we just assume is isotopic emission, but rather from the spectral state which I have just tabulated, it was all third state. So I would rather say that maybe this third spectrum of the sources may be due to inverse quantization of the photons. So these are some references.
Thank you for wonderful talk. It's now open for discussion. Yes,
Is
please.
there any explicit observation of those data?
This particular galaxy I have not checked for, but we have checked for XMM. But in XMM, what is the problem is that we have these 7 sources. Source 1, 2, 3, but source 3, 4 and 5, it was a little bit earlier data, and later data it was not there. Source 3, 4 and 5, it was not able to resolve, and it was detected as a very extremely luminous X-ray source, and it was detected as a single data. But with Chandra sub-second resolution, it was resolved into 3 different sources in XMM. But I have not checked for AstroSat, and honestly,
These are publicly available data.
yes, publicly available, but the last 3 people have not worked that much. So we have worked, and whatever work that has been done with the previous observation I did, we have compared with that.
What could be the best possible site for intermediate mass black holes?
Best possible site.
Yeah.
Okay, with reference to our study, the HLX and the ELX, which I have, HLX I have not mentioned in my talk today, but we have some work in 2019 where we have just detected 7 new HLX. So what are HLX is that they are ultra-luminous X-ray sources whose luminosity is again the lower limit is tended for 41 hours per second. Here I have mentioned the ELX, extremely luminous X-ray sources, whose lower limit is tended for 40 hours per second. So these kind of sources, when their spectrum is very short, then we can always model them as the Dix black body model, and from there the mass estimation is like intermediate mass black holes. We can, this is all estimation. And there have been lots of debates regarding is there any possibility for intermediate mass black holes. But recently, LIGO observation in 2020, I think, right? So they have discovered one intermediate mass black hole. That's what, and one of the speaker, your student also was trying to do lots of work on forming intermediate mass, like 10 to the power 3 to 10 to the power. But in her talk, I have just seen that mentioning 10 to the power 3 as supermassive, right? It was intermediate. Yeah. So in these whole our study, it is the ELX or HLX, the soft spectrum with the soft spectrum.
Yeah, 100 solar mass is fine, but 100,000 at least.
Yeah,
Either I need to do the cluster.
evidence is there for only 100 plus, but from all the study with estimation, we are even sometimes getting about 400. Only observations and later studies we have proved more.
Is there any more question? If no, so let us thank the speaker once more. Oh, one question. Okay, just.
In some of the results, you showed that your NH value is 0.
No, sir. Yeah, the thing is that it's not exactly 0, but the thing is that it's 0.000, but we could not incorporate all those things.
But my question is, even how you are getting these small values of NH? Is it an observation, data analysis artifact, or something else? Because you know that the NH value cannot be that low.
Yeah, so it may be some sort of artifact also, but with these particular models which are available in XSpec, so we are getting very small sometimes.
It's true in some of the models available in XSpecs. Whenever you are using it to interpret your data, this model may not be suitable to use.
Yes, models are not always, we cannot say they are 100% accurate. So,
because this NH value cannot be having these small values.
but somehow we are finding that very small values. So for those ones, we have to again pick up and just inspect it individually.
Yeah. Because in many observations, NH value dictates what luminosity you are getting at the end of the day. Unless
in many of our work,
maybe you can try with some NH value, in particularly those cases, just freeze it and see what luminosity you are getting from there.
yeah, we have tried freezing some parameters, like parameters, for example, for this spectrum, there are 3 parameters. So we tried freezing first parameter, second parameter,
No,
and trying to
improve.
improve.
I'm freezing the NH value.
NH value. Yes.
And then you can try.
Yeah, and when we plot this NH versus LX, there is no particular correlation we are finding. So we have just thought.
I think there is no more questions. Okay, so let us thank the speaker once more for a very interesting talk.